This lesson deals with the VI characteristics of JFETs and their modeling. You can find these notes in the ECE302 ebook in Chapter 4, starting on page 4. What's shown here in the corner is the symbol for an N-channel JFET. If you recall, the channel is between the drain and the source. In this case, it's N material, and the gate is P material. There's a diode between the gate and the source, and really the gate and the drain. That's what this arrow is indicating. Here's the P material, here's the N material. The P-channel JFET will have the arrow going the other way. I've also sketched a more accurate representation of the VI characteristics of an N-channel JFET. I've also marked the regions we talked about last time. The region here where it levels off is called the saturation region. The region over here is called the ohmic region, and then we had cutoff over here. On the next page I'll explain what the pinch-off parabola is, but it's actually the intersection of the ohmic region with the saturation region. You can see that they touch each other where the red dots are. I'll derive the formula for that on the next page. Also note the spacing of the curves as we go from 0 to -1, to -2 to -3, which is our pinch-off voltage. The spacing here is not linear, and we'll take a look at the equations that go with that just shortly. Let's start with modeling the cutoff region. That's probably the simplest to do. Now, in all the regions that we're going to be modeling, the gate to source and the gate to drain diodes are always reverse biased. It's a question about how much reverse bias they are. Is that voltage less than or greater than or equal to pinch-off? If you recall last time, the gate to source and the gate to drain were both less than or equal to pinch-off when we were in cutoff. When this occurs, the drain current is 0, and of course the current coming in the gate is also 0 because it's always reverse biased. So the model is quite simple. It's just simply an open circuit between the three terminals. The voltage across an open circuit can be positive or negative or 0. We need to check that these conditions are satisfied. Is the gate to source and the gate to drain less than or equal to pinch-off if we assume this model? Let's look at modeling the ohmic region. I mentioned last time that the gate to source was greater than or equal to pinch-off, and the gate to drain was greater than or equal to pinch-off, and we were in the ohmic region. If we go back on top here, we can find what the gate to drain voltage is. This picture doesn't have the gate to drain on it, but the schematic does. The gate to drain voltage is equal to the gate source minus the drain source. And that's that equation over here. Let's solve for the drain source voltage. That's going to put that over here. The drain source voltage is less than or equal to the gate source minus the pinch-off. The equation when we're in the ohmic region was found experimentally to be the following. A constant K, which we'll define on the next page, times the quantity, 2 times the quantity, the gate source minus the pinch-off, times the drain source, and then minus the drain source voltage squared. That square term is really showing up right over here on the curve. We're going from a straight line to something that's starting to turn as a square. Let me also explain this inequality. We showed that when the gate to drain was greater than or equal to pinch-off, the drain source was less than or equal to the gate source minus the pinch-off. And we did that because the gate to drain is not shown on this graph, but the drain source is. Let's just check this equation out. Suppose that the gate source is equal to -2, and the pinch-off is equal to -3. So you have -2 minus a -3, which is equal to 1. Whenever the drain source is less than or equal to 1, we're in the ohmic region. And here's where the drain source is equal to 1. We're to the left of this dotted line. You can try it up here too. The value here for the gate source is -1. -1 plus 3 is equal to 2. And here's where the drain source is equal to 2. And then we're less than that or equal to it. That is showing where the ohmic region is. If we're in the ohmic region, the current is this equation. Not as nice as the BJT. You can model that with a current source whose value is controlled by the drain source voltage and the gate source voltage. The voltage across the gate source needs to be greater than pinch-off, but it's the voltage across an open circuit, so we need to check for that. Likewise, the voltage across the gate drain, which is also an open circuit because, again, we've reverse biased these diodes, we need to check that that's greater than or equal to the pinch-off voltage. As we mentioned last time, to be in saturation, the gate source voltage is greater than or equal to pinch-off, and the gate to drain is less than or equal to pinch-off. We showed on the last page that the gate to drain was the gate source minus the drain source on the schematic of the symbol for the JFET. And again, we can solve for the drain source voltage by putting it on this side of the equation. The drain source voltage is going to be greater than or equal to the gate source voltage minus the pinch-off. And this means that we are now in saturation when we are to the right of the dotted line on page 4. Here too, the equation for the current in the JFET in saturation was found experimentally to be that same constant K times the quantity, the gate source minus the pinch-off squared. If we're in the saturation region, Again, we've always got the gate source and gate drain diodes reverse biased, so they're open circuits, and the current follows this equation. And we do have to check that the gate source and the gate to drain follow the correct inequalities. In other words, the gate source needs to be greater than or equal to pinch off, and the gate to drain needs to be less than or equal to pinch off. Just like the BJT, we have transition points, and we can find those by intersecting the models. If we intersect the ohmic and the saturation model, we see that they both have the gate source greater than or equal to pinch off. But when you're in ohmic, the gate to drain is greater than or equal to pinch off, and when you're in saturation, it's less than or equal to pinch off. Equality is where those two overlap. If we take this equation over here and just take the equality part, we'd have that the gate source minus the pinch off is equal to the drain source when we're at the transition point between the two regions. I had marked that as a red dot on the previous page. Also, that would be the case of the gate drain equal to the pinch off voltage. We could use either the ohmic equation or the saturation equation and plug in the fact that this is equal to the drain source. Probably easier here, although you get the same result. That drain current is K times this quantity squared, but that quantity is the drain source voltage. That's why when you plot that on that curve on the previous page, you see a parabolic type shape. You see a squared of the drain source voltage. This is also called the pinch-off parabola. K is in several of our equations, so we need to solve for it. We're going to do that probably the easiest possible, and that's to take the equation either in ohmic or in saturation. The saturation one's a little bit easier, and evaluate it at a point. Probably the easiest point is when the gate source is equal to 0. When the gate source is equal to 0, that drain current has a special name. It was shown as 18 milliamps on the previous page in a specific JFET, but it's also called IDSS. And what that means is that it is the drain to source current with the gate to source shorted. In electronics, when you see a third letter, it's usually O or S, which stands for open or short. If we set this equal to 0, we get K times the pinch off squared, and now we could solve for K. It's IDSS over the pinch off squared. We could also have an intersection of the saturation model with the cutoff model, and I'm going to call that the edge of cutoff. And when you're in cutoff or saturation, the gate to drain in both cases is less than or equal to pinch off. But when you're in cutoff, the gate source is less than or equal to pinch off, and when you're in saturation, it's greater than or equal to pinch off. Intersection is the equality. The gate source voltage equal to pinch off voltage. And when we're in cutoff, the drain current is 0, and if you plug in that the gate source equals the pinch off in our saturation equation, you also get 0. The equation for the gate to drain is the gate source minus the drain source. And again, to be in cutoff or saturation, we're less than or equal to pinch off. So now we can solve for the drain source voltage. That's going to be greater than or equal to the gate source minus the pinch off, but the gate source equals the pinch off, so we're going to get 0. This is really just a line along the x-axis. All of that line is the edge of cutoff. Another curve you'll find in a data sheet is the plot of I sub d versus VGS when we're in the saturation region. Our equation is that I sub d is equal to K times the quantity gate source minus the pinch off squared when we're in the saturation region. And we just showed that K was equal to IDSS over the pinch off squared. These are two numbers you can get off of the VI characteristics. And this is the current when the gate source is equal to 0. And V sub P is the value of the gate source voltage when the drain current goes to 0. The values for IDSS on page 4 were 18 milliamps and the pinch off was minus 3. That's 18 milli divided by 9, which is 2 milli. Plotting that, you get a parabola. Parabola actually continues on mathematically, but we really stop when we get to this point when the current hits 0. This is going to be troublesome for SPICE. It has to find this region given this equation. But the value here where the current is 0 is the value of the pinch-off voltage. It's a little bit easier to read on this curve than the I sub d versus VDS curve. And also when the gate source is 0, this is the value of IDSS. This is called a transfer curve because we got an output current over an input voltage. This will be important for AC analysis. For a BJT, we had an NPN transistor and a PNP transistor. And for a JFET, you can do the same thing. You can have an N channel or a P channel. It's just that all voltages and currents are reversed. I'm going to draw the symbol upside down like I did for the PNP transistor because in electronics we show current flowing from the top of the schematic to the bottom of the schematic. So here is my drain, source, and gate. I'm going to flip the direction of both the voltages and the current. So now the voltage can be between the source and gate, the drain and gate, and the source and drain. Show the current coming into the source and out of the drain. Because the gate current is 0, the source and drain currents are the same. I'll label that over here. Now if you do this, you get exactly the same VI characteristics we had before. It's just that all subscripts are reversed and all currents are reversed. The reversal of the current is on the schematic. The reversal of the voltage is with the subscripts. Now when you do this, you're going to get a pinch-off voltage that's again negative, and a value of current here is now going to be called I sub SDS. It's the current from source to drain with the source to gate shorted. Some data sheets still call it I sub DSS, but it actually be more accurate to say it this way. And this too will be a positive number, just like it was for the N-channel device. Now, virtually no textbooks use this notation. They wind up having everything flipped. They have the curves in the third quadrant, and it's very confusing for a student or for even an engineer to keep all that straight. So I like the idea of just flipping the directions like we did for the PNP transistor. If we reverse all voltages and currents in our equations, then our models will be the same if we do likewise. So to be in cutoff, now the source to gate is less than or equal to pinch off, and the drain to gate is less than or equal to pinch off. The drain current is still 0, but now we're reverse biasing the diode from the drain to gate and source to gate. We'll flip the terminals of the source and the drain. We'll have to check that the source to gate and the drain to gate is less than or equal to pinch off. Likewise for ohmic, now the source to gate is greater than or equal to pinch off, and the drain to gate is greater than or equal to pinch off. Our model will be the same. We're going to flip the source and drain terminal to turn the direction of I sub D around, which equals I sub S, and this will be our equation in the ohmic region. We need to check now that the source to gate and the drain to gate are both greater than or equal to pinch off. Same for the saturation region. Same equation, just simply flip the subscript. Model is the same, which is really a current source describing this equation. Check for the inequalities now from the source to gate being greater than or equal to pinch off, and the drain to gate being less than or equal to pinch off. Our transition points would be the same. The first one being the edge of saturation, where ohmic and saturation come together, and that's where I sub D is equal to K times V sub SD squared. Again, flip the subscript. We'll be able to solve for K the same way, but now we're going to be using the current from the source to drain with the source to gate shorted, divided by the pinch-off squared. And then our edge of cutoff would be the same. It'd be the line along the x-axis, but now when the source to drain is greater than or equal to 0. Now if you learned all the equations for the N-channel JFET, you really have the same equations for the P-channel for free. You're simply going to change the subscript and flip the direction of all currents shown on the transistor schematic. And lastly, if we were to plot the transfer curve of I sub D or I sub S, they're the same versus now the source to gate voltage, we would again get a parabola. And again, this parabola will continue on. But the part that we're looking at is over here when we're in current saturation or just saturation. And this point where we hit 0 current is the pinch off, and where we have 0 source to gate voltage is I sub SDS. And these are the VI characteristics of JFETs and their modeling.